Hey everyone, welcome to Intro Physics, the online version. My name is Tim Sullivan. I will be your teacher for this semester. Um, so the first thing that we wanted to get into and we want to talk about, since we are in a science class, we are doing physics, we want to talk a little bit about what we mean when we're really trying to do science, and we want to kind of talk a little bit about the process of that. So a very simple way to put it would be that when we're doing science, if we want to do this stuff effectively, if we want to have this stuff be useful to us, what we want to do is we want to create models to make testable predictions. So it's kind of some fancy phrasing, but it's actually probably a concept that you're all familiar with already, whether or not you realize it now. So the first thing you can think of, again, when we're talking about we're going to be creating models, and of course we're going to be doing that in this class as well. We'll be throughout the semester coming up with and using some very simple mathematical models for how stuff moves around. But just in general, when we talk about making these scientific models, probably one of the first things you're used to when you're talking about models would just be like little model train sets or model plane sets or whatever the hell it is. Anything like that that you can think of. The reason these models are useful is, again, they're not necessarily an exact representation of what's going on, but it is a good starting point to learn about how a certain system works, right? So again, if you want to explain to someone how trains work and they've never heard of a train, they don't have any idea of it, but you have a model train set on hand, that can be a very useful tool to kind of teach them a little bit about what is going on, right? It's not an exact representation of an actual full working train or anything like that, or full working plane, whatever it happens to be. But it is a model, it is a representation of that system, and it is useful when trying to learn about it. So how does this tie in then to science? So again, what we're going to be doing is we're going to be kind of creating models. We're going to see how those models, what those models do under different circumstances, and we're going to try and make predictions with them, right? Before we get into that, though, we can kind of come up with one simple example of a scientific model that you guys have probably all seen before. So if I draw a picture that looks something like this, put these little dots here for my nucleus, and then I have some electrons orbiting in this way. Not a very good picture, but you get the idea. You've probably all seen a picture that looks something like this, right? This is a very simple model of an atom. This is actually called the Rutherford model of an atom. And in this model, what we're saying is this is how we are modeling, right? If we use the word model as a verb, this is how we are modeling the structure of an atom, right? So you've probably seen a picture that looks like this, and this model, it's a very simple model that we have. We put our nucleus at the center, and we have our electrons in these orbits around it. And in this model, it's kind of analogous to how you could have the planets orbiting the sun. And so what we mean by this with this model is then we can actually use this. We can say, okay, I can actually like physically build this, or I can draw it or whatever. I can do my math with whatever this is, and I can say, okay, if this is what the actual structure of an atom looks like, how will atoms behave when I, poke it or prod it or twist it or bend it in some kind of way, right? And this model will give you some sort of predictions from that. You can go and you can actually find some real atoms. You can try and test those predictions, right? So this is not an exact representation of an atom, but it is kind of a model of an atom, right? It is kind of one way you can model an atom and see how that might work and see how they might react under different circumstances. Of course, another model of an atom that you may have seen before, you may not have, that's okay too, is something that looks like this. You can have maybe the nucleus looking roughly the same with our little protons and neutrons in there, and then we have some sort of cloud of electrons orbiting it in this way. So instead of having these kind of fixed point particles for these electrons, what we actually find is that you can actually model these electrons as this kind of cloud that is kind of just spread out around the nucleus at all times, right? So these would be kind of two different competing models, right? And they'll kind of, as you can see, if I were trying to construct these models or something like that, or try and do the math with these models, you will get different predictions. You will get different types of results for it. Actually, as it turns out, this second one that you may have seen before, this second one is actually the more common version, is a more accurate version of what is actually going on with the structure of an atom, right? So these are just kind of two simple models that you can visualize for what we mean by this, right? Neither one of these is exactly how an atom works. We'll kind of get into a little bit more of this later on. Certainly, you'll do more of this if you deal with Phys 2 a little bit, kind of talking about what protons and electrons are and how they work. But for now, this is kind of an example to kind of tell you what we mean when we talk about these scientific models, right? So, but in physics, though, what exactly we're going to be trying to doing in this class, we're not going to be too worried about the exact structure of atoms just yet. That'll be later on. That'll be in different semesters if you go on and you take more physics classes. For this intro physics stuff, what we're going to be doing, we're going to be building models to kind of simplify um, certain things, and we're going to be talking about the motion of these objects, right? So in this case, when we're talking about physics, right, it is kind of this catch-all term. Essentially, physics is the study of how the universe works. If you want to break it down from that, which of course, you know, everything being in the universe, you can in some sense say that physics is the study of everything. We're not going to focus on everything, though. We're going to keep it nice and simple for this semester. We're just going to be focused on how things move around. That's what we'll be doing in Phys 1. So yeah, so again, what we're going to be doing then, we'll build some simple models. We'll kind of approximate certain circumstances and see what's going on, and we'll see how these different objects move around. So one thing that we're going to all need to agree on before, though, if we're going to actually do any physics or do any science, is we also need to agree on certain physical quantities, right? We're going to have to measure certain quantities. If I want to tell you how stuff moves around, of course, you probably want to know how long did it take, how far did it go, that kind of thing. And so we do need to agree on a unit system that we're going to be using for the rest of the semester. So the basic units that we'll be using, that we'll be dealing with this semester, we have the meter, to denote distance, right? Stuff that's in, you know, however many meters we've traveled, something like that. We have kilogram. This is going to denote how much mass something has, not necessarily how much it weighs. That'll be a little bit different, right? So we have meters for distance, we have kilograms for mass, and again, we'll get more into these details a little bit later on, but for now you can think of mass as just a measurement of how much stuff there is, right? Not necessarily how much something weighs. That'll be a little bit different. That'll kind of depend on where you are. We have the second to denote time, right? However many seconds have passed, that's how much time has passed, so on and so forth. And then if you really want to get into the details of it, we're not going to use this one this semester. If you take Phys 2, you will. But our last kind of fundamental unit that we would use, something called the ampere, right? This one, though, this one is for Phys 2. If you take Phys 2, you'll deal with this one a lot. The rest of these, though, is what we're going to be using here in Phys 1 a lot, right? We're going to be using the meter, the kilogram, and the second. We're going to be talking a lot about how much stuff do I have. Oops, Phys 1, there you go. We're going to be talking about how much stuff do I have, where is it going, how far is it going, how long did it take it to get there, so on and so forth, right? So we do actually have, it's just some trivia for you. You don't need to memorize this part just yet. We do have good definitions of where all these things came from. We do have a good definition of what 1 meter is. So the original definition of a meter used to be 1/10,000,000th the distance from the equator to the North Pole. So if you do your quick math, what you'll see is that it used to be that the circumference of the Earth was defined as exactly 40,000 kilometers, right? So 1/10,000,000th the distance from the equator to the North Pole. That would be, so if that's 10 million meters, that would be, you know, divided by 1,000. You would get 10,000 kilometers from the equator to North Pole, which is of course 1/4 of the way around. That's a pretty close estimate. It's off by a very small amount. We have a more consistent definition of a meter now. Is actually based on a certain fraction of the distance that light travels in 1 second. So that's kind of what our definition of a meter is. So that's going to be important. Again, just from a philosophical standpoint, we want to make sure, you know, if I do an experiment now and I publish a paper about it and I say I threw a ball 10 meters, right? Not a very exciting experiment, but you get the idea. If I publish that and I'm like, yes, this is great work. I've thrown this ball 10 meters. 200 years from now, when I'm dead and gone, you can't get a hold of me anymore. Someone reading that can say, okay, I know exactly how far this guy was able to throw the ball, right? So we do want to make sure that we do have these nice consistent definitions across time, right? We do actually also have a good definition for a kilogram now. Finally, this is actually somewhat recent. Again, this is all just science trivia. You don't have to worry about this too much. I'm not going to quiz you on it. The kilogram, it used to just be for a very long time. The definition of a kilogram was, there's a certain museum, I believe it's in Paris, somewhere in Europe, where they had a chunk of stuff and they said this is a kilogram, and that was basically it. That was all we had. That was our definition of how much stuff a kilogram was. So of course that kind of presents its own problems. That's a little bit difficult to reproduce. You got to make sure that chunk of stuff that you have there, that chunk of metal that they had, is nice and pristine, not getting any chipped away at anything like that in any sort of way. Um, Now we do have a better definition of the kilogram. That it's a little bit more complicated. It's not as easy as just saying a fraction of the distance at the speed of light, or that the speed of light travels in a second. The kilogram is a little bit more complicated. We don't need to worry about what the exact definition is, but you can rest assured there is a strict, consistent definition of the kilogram that will still hold up in a couple hundred years from now, and even 1,000 years from now. So for the second as well, we do have good definitions for that. The second, it used to be defined as 1/86,400th of a day. The problem with this is, right, if you do your math, right, you have 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, so on and so forth. 86,400 seconds is about how many seconds there are in a day. The problem is that the Earth's rotation is actually slowing down. It's a very slow effect, but if you go back, if you get in your time machine, you go back a few million years, you find that the length of a day would actually be about 23 hours or something like that, depending on how far back you go. And if we go forward in time, we'll see that at some point in the future, the length of a day here on Earth will be about 25 hours. So we don't really want to use a fraction of the length of a day, since the length of a day is changing. So now what we do instead is we have a second is defined as a certain number of vibrations of a cesium atom. So it's about 9 million vibrations of a cesium atom when it's in a certain state under certain conditions. Is how many is however long that takes is defined as 1 second. So have you ever heard of something? If you ever heard the term like atomic clock for like a really precise clock, this is what they mean, right? They're using these kinds of cesium atoms to kind of keep track of this time down to these very small, very precise fractions. So yeah, so these are again the different units that we'll be using. We have meters, we have kilograms, and we have seconds. Again, if you take Phys 2 next semester or whenever, you'll deal with amperes. This kind of has to do with electric current, has to do with some charges moving around and all that kind of stuff. We don't have to worry about it for now. But for now, meter, kilogram, second, we're going to be using those quite a bunch. So along with this, the first thing that we can do then from like a problem-solving standpoint, we can go over some unit conversion and dimensional analysis type stuff, right? So if we have all these units, we do want to be able to make sure we understand how they work and how we can convert between different units, right? So one really quick example we can do then is something that looks like this. We can say, very simple problem. This will be the easiest problem that I'll give you all semester. Easiest example will do how many kilometers. What's a kilometer? 1,000 meters, right? Kilo, put that on there. 1,000 meters. How many kilometers is 80 meters, right? So how do we go about doing this? Nice, simple unit conversion problem so that we have. So we have 80 meters. This is what we start with. Need to multiply it by 1, right? So essentially what that would be is it would look like this. We want it in kilometers. We put 1 kilometer up top here. How many meters are in a kilometer? As I said before, we have 1,000 of them. So the units themselves will cancel out, and you can add, subtract, multiply, and divide as long as you keep track of your units safely, and this will work out just fine. So we have the meters will cancel out. So the meters divided by meters cancels out. 80 times 1 is 80 divided by 1,000, and you get 0.08 kilometers. Very simple, very quick and easy unit conversion problem. Hopefully this is a review for some of you. If it's not, that's all right. That's just fine. I'll be teaching this as though you have not seen this before. This is the stuff we'll do at the beginning. We'll go kind of quickly through it, and then we'll move on to some more exciting stuff. But you do want to make sure you understand how this unit stuff works. It is very important to keep track of your units when you're solving these more complicated problems. If it's a very good way to check, right? If at some point later on the semester I ask you, how far did this car travel, and you say 3 seconds, that's probably not good, right? You probably messed up your units somewhere, right? If it's a distance, you probably want to make sure that your units do work out to staying in meters. So we can make this a little bit more complicated now. We can move on. We can do a different example. So it's going to be our last example that we'll do of these unit conversion type problems. So we can say, we're going to add a couple more terms in here. So we're going to say, suppose you drive 10 kilometers in 20 minutes. What is your average speed in kilometers per hour and in meters per second. So we want our average speed, right? So we haven't really talked too much about speed yet. I haven't given you a strict definition of it, but we already have some sort of idea of what that might mean. Basically, how fast we're going, how much distance are we covering in a certain amount of time. So we have, suppose we drive 10 kilometers in 20 minutes. What is your average speed in kilometers per hour and in meters per second? All right. So the first thing we want to do is let's just find our average speed in the units that we're given. We're given 10 kilometers, we're given 20 minutes. How do we figure that one out? So we have our average speed, we're going to use V, is going to be 10.0 kilometers divided by 20 minutes, right? We went 10 kilometers, it took us 20 minutes. Our speed, as we'll see, is going to be how much distance we covered divided by how long did it take us. And so this ends up being 0.5 kilometers per minute. It's not usually how you would measure your speed. You're probably used to miles per hour, kilometers per hour, right? Depending on what country you're in. Of course, if we're using our basic standard units that we have, that I kind of outlined for you here earlier, the common speeds that we will use will be in meters per second, right? So right now what we have is we have kilometers per minute. What we were asking for is kilometers per hour and meters per second. So let's go ahead and let's figure out how we're going to convert that. So we already have it in kilometers per minute. Let's go ahead and convert this to kilometers per hour. So here we would do something that looks like this. We would say V equals 0.5 kilometers per minute, and we need to convert now this to kilometers per hour. So again, we want to essentially multiply by 1. How many minutes do we have in an hour? Minutes in 1 hour. So we have kilometers per minute. Minute cancels with minutes, and we end up with 0.5 times 60, which is of course 30 kilometers per hour, right? Now if I want this same speed, but I want it in meters per second, how am I going to go about doing that? So I have it in kilometers per hour. Now I need to convert both the kilometers to meters, and I need to convert the hours to seconds. Again, just make sure to keep track of all of your units. If you write them out every time and you actually do the math where you're multiplying, dividing, sorry about that, microphone cut out. So if you're adding them, if you carefully multiply, divide, add, and subtract your units correctly, just like you would with all of your other quantities, this will work out every time. So let's make sure we do this correctly. So we have our speed is 30 kilometers per hour. So again, we multiply this by 1. We have 1,000 meters divided by 1 kilometer at 1,000 meters is the same as 1 kilometer. This is what I mean by multiplying it by 1. So this will convert our kilometers to meters. Then we can say 1 hour also 3,600 seconds, right? So 60 seconds in a minute, 60 minutes in an hour, 60 times 60, 3,600 seconds in 1 hour. We do this, what do we get to our seconds? We end up with, okay, so the hours do cancel out, the kilometers do cancel out. We're ended up with meters per second, multiplied by 1,000, divided by 3,600, and what we get is about 8.33 meters per second. So this is what our speed would be, right? We have it in 3 different speeds. We have 0.5 kilometers per minute, we have 30 kilometers per hour, and we have 8.33 meters per second. So one last thing to know about this, with our unit conversions, I'll talk a little bit about significant figures. You probably have heard that term before. It's again just basically how many decimals am I asking for. Usually I'm not going to be too concerned. In this case, you can see how many significant figures do we have. We had, since we do have this decimal here, we have 1, 2, 3 significant figures, right? In this case, we only had really 1 significant figure, if you want to be precise about it based on how I wrote it. But for the most part, I'm not going to be too much of a stickler about it. Don't give me 1 sig fig. You're going to need more than that. Don't probably give me more than 3, though. Maybe 3 or 4 is fine. But if you write out a bunch of, if you give me like 12 decimal places, those aren't meaningful, right? Those last probably 9 or 10 of them aren't going to be meaningful. So I'm not going to be too much of a stickler about it, but just don't go crazy with it one way or the other. So yeah, so that'll do it for our unit section. And yeah, so we'll start kinematics next after this.